Time is presently 17:30. I have talked about everything I care to talk about in chapter 22. So, I have selected some problems from the end of the chapter to talk about. If it's not enough, I suppose you could ask me some more questions about them. Alternatively, let's see, we are recording, right? Yeah, good. Alternatively, we can ask questions from the whole chapter. Son of gun. That's just the whole chapter. From the whole semester, considering that next Thursday we have an exam. I am working on sample exam. I have presently finished up the equation sheet. And so as soon as I'm done with class, I'll be writing up the questions for that. And so hopefully, hopefully before I leave here, you'll have a copy of that. If you don't have a copy of it, you'll have it tomorrow. Anyways, so questions about what we're doing today? I thought it was pretty clear. Delightful. So, these are the questions I have selected for my own various reasons. Ooh. Let's go over there. Alrighty. Alright, so the one I had intended to finish with yesterday was number 65. Oh. So we got a step-down transformer. If I can do an in right. Step-down transformer in the ratio of 1 to 8. Alright. He's used, let's see here. Step-down transformer is used with an electric train to reduce the voltage from the wall receptacle to a value needed to operate the train. And when the train is running, the current in the secondary coil is 1.6 amps, whereas the current in the primary coil. So, with a current of 1.6 amps, that is not a whole lot. Quotation marks, so not a whole lot. For a model train, that sounds like a lot to me. For a commercial train, that sounds like not much. So I don't know what train this is, but we'll go ahead and go with it. Alright, so let's see here. Why don't I go ahead and pull up a little bit of the equation sheet that I have here and copy that in. Let's see here, print screen. I would like to grab this much right here. Copy that. Don't do that. Oh, you got an extra window. This one. That one. Go away. Discard changes. Thank you. Control V. There we are. Give me a lot to move. Put it there. And the R. Set down. Okay. And delete that. Alright. Not that one. R. Select nothing. Thank you. And back pencil. Alright. So 1 to 8. I in the secondary is equal to 1.6 amps. Oh, and I said minimize that. Thank you. Alright. Alright, so right here is the equations we need. So we're stepping down from V primary over V secondary in the ratio. Secondary needs to be down by a factor 8, so primary is 8 to 1. And then so let's see here. So V2 over V1 is equal to I1 over I2. So these are in opposite orders. So it'll be I secondary over I primary. It would like to know what is I primary. Okay. Yes. Current in the primary coil. Alright, so we're stepping down 8 to 1. So that means that this is equal to, secondary is 1.6 amps divided by IP. And that'll be equal to 8 to 1. Alright, so I want the IP. It comes up, 8 goes down. Multiply by IP over 8. 8's go away. IP goes away, divide by 8. So 1.6 amps divided by 8 is equal to IP is equal to, looks like about 0.2. Yep, 0.2. 0.2 amps. Questions? Make sense? Alright. Hearing no questions. Alright. Number 63, you want to do next? Or, yeah, let's do 63 next. Alright, hold on. There. Alright. So I grabbed number 63 for a particular reason. Might discuss it for a little bit here soon enough. So we have an AC load on one end. It goes through here, and it goes da 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 da. Go back over here and up to here. Through our through our transformer. If I can make a good transformer, close enough. And then we have a load over here. We'll try again. We have a load over here. There we go, that's better. Over here, coils on this side. Alright. This is 14 ohms. All the wire nonsense on this side is 56 ohms. Alright. So the resistance of the primary and secondary coil of the transformer are 56 ohms on the primary, 14 ohms on the secondary. Both coils made from lengths of the same copper wire. The circuit turn of each coil has the same diameter. Find the ratios in S to NP. In S to NP. Alright. What in the Sam Hill's going on here? Alright. So the best that I can figure about what's going on here is that we've got some impedance matching going on. Turns out that power is best delivered when the impedance on both sides of a circuit are the same. If you were to look at the details of audio equipment, you can find that the impedance, the resistance in a line out socket, you know, the thing you would plug your headphones into, come in, I think the common ones are 2, 4, and 8 ohms. And your speakers can be found in with resistances of 2, 4, and 8 ohms. And you can deliver your power to the speakers best when the impedance matches. So you want to put an 8 ohm speaker on an 8 ohm resistant socket there. And with 4 ohms on a 4 ohm, and so forth and so on. So this, if everything goes the way I think it will, what we're actually looking for is we got power on one side equal to power on the other. Power on the primary, power on the secondary. We have but we also need to grab from our equation sheet, where my equation sheet go, the power for a resistor. Why did I do that? There it is. Is that equal to, in particular, V square on R? Oh, that's not what I said to do. Alright. So we have that V on the primary squared over resistance on the primary is equal to V on the secondary squared divided by resistance on the secondary. Well, we know what these R's are, so now I can rearrange these guys to get these guys here, invoking this particular equation right here. So this will be equal to V secondary divided by V primary. Alright, so secondary is on top. I'm going to multiply by our secondary and divide by V primary squared. So they'll cancel that guy there and that guy there, and this guy will cancel that guy over there. Ta-da. And we end up with V secondary squared divided by V primary squared, and that is equal to let's see here, our secondary divided by our primary. And then we need to get rid of these squares, so we take the square root. And so we end up that this is the square root of our secondary divided by our primary. Punch in our values. Square root of 14 ohms divided by 56 ohms. Calculator, what is the value? Square root of 14 over 56 is 1/2. So there's the ratio. This was 60. Don't go drive over there. This was 63. Questions? Delightful. Alright. 67? Yeah, 67. Try again. There we go. Alright. 67. Alright, we have some generator over here. It is making 1.2 times 10 to the 6, 1.2 times 10 to the 6 watts. Alright. Which is kind of small for a generator. For a power plant, anyways. It's big for a house generator, but it's pretty small for a plant generator. That's 120 kilowatts, and we're pretty good at making things that'll go up to gigawatts. So it's kind of small. Anyways, next nearest place for Earth is to be used in our town is a distance of 0.7? No. Total 7 kilometers, right? Where we go? Yeah, whole 7 kilometers. Power needs to move a whole 7 kilometers from where it's generated to where it's being used. Each of the 2 wires, the compressed transmission line has a resistance per kilometer of 5 times 10 to the minus 2 ohms per kilometer. So resistance per length is 5 times 10 to the minus 2 ohms per kilometer. So, part A, power dissipated in transmission lines at 1200 volts. B, a 100-to-1 step-up transformer is used to raise the voltage before the power is transmitted. How much? Same question, but this time same, but we're now transmitting at 100-to-1, so that's 1200 and some more zeros volts. So 120,000 volts. So, alright. To do this, first thing I need is my resistance. Resistance is equal to, well, take my resistance per length of 5 times 10 to the minus 2 ohm per kilometer, multiply it by 7 kilometers. Those match. And so we get an answer of 5e minus 2 times 7. Right? Make sure I'm reading it right. 7 kilometers per kilometer. Yep. 5 times 10 minus 2. Yep. Go. So it's not a whole lot of resistance. 0.35 ohms. Okay. So then we have this power is equal to, well, let's be V squared on R. Alright. Do I have it up here? No, of course not. Oh, it's right here. V squared on R. Okay. So it smells a little funny. Oh, and there's 2 of them, so there's 2 wires. Right. Let's see here. Let me check that. Make sure I'm reading this right. Each of the 2 wires that comprise the transmission line. Well, I suppose that's for going out and coming back. So I suppose we have to multiply it by 2. All right. We go out and we come back. All right, fine. So that'll be 0.7 ohms. Really? Okay, so V squared on R. Okay. Alright, well, interesting. This is not going the way I would expect it to. 0.7 ohms. This here, 1200 squared divided by 0.7. Oh. Wait, what? 1, 2, 3, 4, 5, 6. There's some weird stuff going on here. Aiden, you're gonna need to turn your volume up.
Okay. Sorry, my mic actually was up on accident.
Yep.
Why is the resistance doubled when you have 2 wires instead of half? Because you would think that it would let it flow through twice as much.
The thing is that it would go out through the one wire and then it has to come back through the same wire, through a different wire.
Oh, okay.
So
it's not sending 2 wires the same way. Okay,
yeah.
Makes sense.
Yeah, which is not actually how power is transmitted, because it's actually sent in 3-phase for mathematical for good engineering and mathematical reasons and whatnot. They're just not telling you what 3-phase is all about, which is very kind of them. Oh, this, okay. All right. So this, I went straight for the wrong way to do this problem. Yes. So what I've got here is yes, but no. So we're told the power that this thing can produce, and the voltage is producing it at. So that means that will imply a current. So power is equal to IV, which implies that our I is equal to P over V. And so that will be 1.2 E6 divided by 1200. And so we get current of 1 kiloohm, killiamp. There we go. Now we can do P is equal to power dissipated here in our wires is I squared R. So that'll be a killiamp squared times the resistance of this wire of 0.7 ohms. And so that'll give us 700 watts. Alright, in this case, P equal IV implies that the I, P, divided by V will give me, scroll up and put 2 more zeros into that. Something that's 100 times smaller, so 1,000 divided by 100, that'll be 10 amps. Now we use the same equation. Power dissipated in the wire, I squared R. And well, that's the same 0.7 amps, but now we're down to 10 amps squared, 0.7 ohms. So that's 100, well, whatever, 0.7. And now we're down to 70 watts dissipated in the wire. And that was what I was trying to talk about at the end of class yesterday, about why we were jumping our, pushing the voltage on our transmission lines up so that we would dissipate less power in the transmission lines. Make sense there?
Yeah.
A little bit of information. Was that?
That makes sense to me. Yeah.
Good. A little bit of information about how transmission lines actually work. Just for kicks of it. Not relevant to this chapter. Might be in the next one though. So we have 3 wires that go out from our generator, and they all go out to here, wherever they're going, and we do it in 3-phase. These guys go out like so, and then this guy is 120 degrees later, so it starts about here. Whatever it is, and this guy will start over here. And so when you add these guys up at this end here, they just the sum of them. So this would be the sum of the currents. So I1 plus I2 plus I3 is equal to 0. And the power delivered, 1 plus power 2 plus power 3 is constant, which is, in my opinion, pretty clever, because the alternative with 2-phase, which is what our houses run on, if I can do this right. Nope, of course not. Let me put down the oscillators first. Closer. There we go. Close enough. We do this. All right, still still add up, but our power is no longer constant. And we have to actually make it go back the way it came. Whereas this here, we're just delivering current straight up all the time. So this is more efficient when it comes to power and current and copper wires and all that, than this is here. But the 3-phase is not worth it in a house, so we end up with 2 phases in a house and 3-phase in commercial places, like, not commercial places, industrial places, and they have other stuff that you worry about as well. Which we'll get to talk about in the next chapter a little bit. Anyways, that's a different day's problem. The actual math of it is another day's problem. All right. 25. Oh yeah. $25. Right. Counts as medium. So we have a copper rod sliding on 2 conducting rails that make an angle of 19 degrees with respect to each other, as in the drawing. Come on, and then here. Please show me an angle. let go. Right about close enough. Boom. 19-ish degrees. And then we have a copper rod. Let's make a straight line. Good enough. There we go. We have a magnetic field going into the paper. Copper rod is going to the right with some velocity. V is equal to 0.6 meters per second. B is 0.38 Tesla. Rod's moving, constant speed to the right, 0.6 meters per second, 0.38 Tesla uniform magnetic field, perpendicular field of plane paper. Determine magnitude of the average EMF in the triangle during a 6-second period after the rod has passed point A. So we're looking for EMF. EMF average in 0.6 seconds. Right? No, sorry, not 0.6 seconds. Average EMF. I'll make it a little better. For time of 6 seconds after, if I can spell right, after passing vertex. Okay. So, well, it's not. I'm not going near these fences as I thought it was going to be. So we got an EMF is equal to minus in change in magnetic flux. Try again. Magnetic flux after change in time. Okay. So, given that n is not mentioned, that is 1, so that's minus. And so we're going to have a change in magnetic flux over change in time. We know the amount of time. So how far to the right do we go? Okay. So we're moving 0.6 meters per second, so that'll be 0.6 times 6. 6 times 0.6 is 3.6 meters on this side. Which implies we need to find out what the area is here. So this is going to be minus B change in area over change in time. And then we can get this side here. Because it's 19 degrees, we can figure out what this guy is. So that will be opposite over adjacent. So opposite over adjacent is equal to tan 19 degrees. We have the adjacent, so to get the opposite. So this will be 3.6 meters. Tan 19 degrees. And then the area of a triangle is 1/2 base times height. So then this will be minus B is 0.38 Tesla. The area is 3.6 meters squared. Tangent 19 degrees, 1/2. So 1/2, base is 3.6, height is 3.6 tan 19 degrees. So I've taken it all in, and then this will be in 6 seconds. Alright, average EMF. Push that on my calculator, 0.388 times 3.6 squared, tan 19 divide by, not that, and the 19 divide by 12. Average EMF is 0.141. 141. That'll be volts. This is an average. Can we go a little fancier about it? Possibly. The area is going to be 1/2 base height. No, I don't think, not in this class. So this will be the base, 1/2, velocity time, and the height will be velocity time again, squared, tan 19 degrees. And so when we get all done with this, that'll be, we'll have some constants in a time squared. So 1/2 v squared tan 19 degrees, and then we get t squared here. It's possible you can figure that out, but obviously it's not required in this class. We can do it anyways for kicks of it. So we can find that the EMF is actually exactly equal to, let's see here, minus 0.38 Tesla. You can figure it out. It's similar to turning an acceleration into a velocity kind of thing. So it's possible, but it's definitely not required. 19 degrees. And we get T here. And I think that's it. So this will be exactly correct. So if it has a function of time, so this because it's asking for an average, this is the actual answer we're looking for right here. Average. This is getting fancy. That's technically calculus. Let's not go there. So that was 25, 35. Oh, 35 was not the one I wanted. I'm a liar. I have this. Come on. I wanted to pick the one that went with that picture there, not the one underneath it. My apologies. I'm at 34. No, I'm on road drive. Thank you. Oy. So, we have a loop. We have a loop of wire with a resistor in it, sitting next to a wire with some current in it, going that way. Let me put it on the other side. Current goes that way. So we have a drawing showing the straight wire carrying a current I. Above the wire is a rectangular loop that contains a resistor R. If the current is decreasing in time, what is the direction of the induced current through the resistor R? Clockwise or counterclockwise? Okay. So, we have an I producing a magnetic field. I is going to the left. We take our right hand, put our thumb in the direction of the current, curl it around, and I find that the magnetic field on top is going into the page. Like so. Alright. So, it's increasing going that way. But I is decreasing in time. Okay. So if I is decreasing in time, that means the B is also decreasing in time. Well, Faraday's law and Lenz's law wish that the magnetic field is unaltered. And so they will oppose the change to the magnetic field and reinforce it. So we have a B like so. It turns out that because B is decreasing with time, that implies that B induced to reinforce it is pointing into the paper with it. Take our right hand, thumb goes in the direction of the B field, curl it around, and we find that our current to reinforce it, however, there we go, must be going clockwise. I is clockwise. Questions? Make sense? Delightful. That might not even be one of your homeworks. Number 20. Okay. MRIs. MRIs kind of have a special place in my heart. Moment. Mostly for the fact that when I was in elementary school, primary school thereabouts, about the 5th grade or so, I had a brain tumor, and we found it with an MRI machine, and I thought they were the coolest things ever. And when you lie one and have an MRI done, if you like your rap, you might like them too, or your beatboxing. They're very good. They're very good drum kits. Not sure if I care to discuss the physics of what not sure I care to describe the physics and the math and whatnot of how they actually work. But they are fascinating machines, and somebody has done a lot of work on them. So we have an MRI machine. So we have a big old coil. We have a big coil of superconducting wire. And so we get a magnetic field in there. And then we stick a person in it. I made their body too long. Oh, come on. There we go, close enough. Like so. So we gotta be field in here. Okay. Let's get a little bit more to the right. We are told that this magnetic field is a main magnetic field of 1.5 Tesla. They vary the magnetic field in certain ways so that when they pluck your atoms, they can pull out the signal from a particular one and know where it came from because of the variance in that magnetic field. And so some atoms down here will sound slightly different from your atoms up here, and so they can tune it and figure it out. But we'll just consider the main contribution, the monopole, 1.5 Tesla. Alright. MRI machine is a medical technique for producing pictures of the interior of the body. Patient is placed within a strong magnetic field, which I have drawn here. Our safety concern is what would happen to the charged ions in the body if the equipment fails and the magnetic field is shut off. An induced EMF could cause these particles to flow, producing an electric current within the body. Suppose the largest surface through of the body through which flux passes has an area of this much. So our patient here has an area somewhere in here with an A in it. The A is equal to try again. 0.032 square meters. That is parallel to the minute. It should be perpendicular to the magnetic field of 1.5 Tesla. Determine the smallest time period during which the field can be allowed to vanish. If the magnitude of the average induced EMF is to be kept less than, EMF must be less than or equal to 0.01 volts. So, all right. So, and time? Let me figure that out. Oh, wait, let's run for it. Okay. So, EMF is equal to 10 millivolts is equal to change in magnetic flux over change in time. This is the thing I'm looking for right here, the change in time. Change in time is equal to, well, this guy here, what's going on? He's going from whatever it is to 0. So 1.5 Tesla through the area, 0.032 square meters, divided by 0.01 volts. All right. 1.5 times 0.0332. So that's 0.048 Weber divided by 0.01 volts divided by 0.01. And so we get that this is 4.8 seconds. This sounds like somebody's made up a funny question. Somebody's made up a question that doesn't make a heck of a lot of sense in my opinion. Maybe I'm wrong in this one. But I do know that MRI machines come up with emergency shut-off questions where they will quench the coils if things go south quickly. Things where somebody has screwed up badly, like somebody brought in an oxygen tank into the MRI machine, and despite the fact that there's a metal detector right there at the door, screaming his head off over them, having brought in this oxygen tank, it goes in anyways, and it goes in and whacks the patient. Patient is not happy. They are in a world of hurt and dying. They are not waiting 4.8 seconds. So I don't know if they really care that much about this. Anyhow, that's a switch that does exist. I'm pretty sure they ain't waiting 5 seconds to make sure that they aren't generating 10 millivolts of EMF across the patient. I think they want it off now so they can start taking care of business because somebody screwed up badly. Anyways. Yeah. Alright. Number 4. All right. So, number 4. Oh, yeah. This is an interesting one. Or I think it's interesting. Time. Let's see. Go take go to 4 or 17 first. Let's do 17 first. I know exactly what I'm doing there. So I'm pretty sure I can do it in the 7 minutes before the hour of class. So let's do that first. Number 17. So we have a triangular prism. That's a 3, 4, 5. More particularly 0.4 meters, 0.3 meters. So that means this side is 0.5 meters. And it goes off this way, and then it comes down. It goes over here. And this is 1.2 meters. And we have a magnetic field going this way. B. A 5-sided object whose dimensions are shown in the drawing. 5. 1, 2, 3. Yep. 5-sided object, better known as a triangular prism, whose dimensions are shown in the drawing. Placed in a uniform magnetic field. Magnetic field has a magnitude of 0.25 Tesla. And points in the positive y direction. To the right. Determine. You want to know magnetic flux through each side. Okay. So, that explains why it's a medium. Okay, so for the magnetic field, magnetic flux for front, bottom, and back, this is equal to B times A times the cosine of the angle between B and A. Alright, B, A, and the cosine. I've grabbed each three of these for a particular reason. That reason being is that the area normal of each side is perpendicular to this magnetic field. So the front side has this A pointing at us while the magnetic field goes across it. The bottom's normal is pointing down while the B goes across it. And the back is pointing away from us while B runs across it. So in each one of those, that's 90 degrees. Cosine 90 degrees is 0, so this is 0 for all of them. For all three of those. Okay. Delightful. Alright. Then we have the magnetic flux, B, for the left side. Alright, so B is 0.25 Tesla. The area of this, well, that's 0.3 meters up and 1.2 meters back. Put the Tesla there. 0.3 meters on this side going up and 1.2 meters going back. And then we have the cosine of the angle between the surface normal, which is to the left, and B, which is to the right. Oh, well, that's 180 degrees. All right, calculator. Where did my calculator? There it is. 0.25 by 0.3 by 1.2. That is minus 0.09 Weber. Okay. And now, for the magnetic flux on the slanted side. Okay. Again, B is 0.25 Tesla. The surface area, well, that'll be 0.5 meters on one side and 1.2 meters on the other side. And then we have cosine of an angle between A and B. All right, 0.25 by 0.5 by 1.25. Yeah, okay, 0.15. 0.15 Weber. That's not the abbreviation, Weber. Cosine theta between A and B. Okay. So we have if I can draw a better triangle, good heavens. Alright, so we have a normal going this way and a B field going that way, and we need this angle here. Alternatively, we need, oh come on, there we go. We need the cosine of this angle, and so it'll be the alignment between this guy and that guy, and so all right, so Alright, let's see here. So that would be let's do a little bit of trigonometry here. That's 90 degrees there. And so this is the theta we're looking for. And so this phi here is the complement. By parallel angle theorem of some sort or another, this here must also be phi. This is a right triangle over here. So this angle here is our theta. We want the cosine, which is the adjacent. So this side here is 0.3. And the hypotenuse is 0.5. Come on. There we go. Okay. So I can actually replace my cosine with that. And so that'll be 0.15 Weber. 3 over 5. Okay. So that'll be 0.09 Weber. Oh, look at that. The left side, B left, is minus 0.09 Weber, and the right side is 0.09 Weber. How delightful. I believe there's something to be said for this from I was thinking Amps law, but that says circling it with a loop rather than with a surface area. So it's not nearly as interesting as I thought it was, but it's a thing.
Which side is which? Because you just kind of said front, bottom, back, and I'm not, and also left and slant. So like I'm not sure which one you're labeling.
So this is front. That's front. This is slanted. The back side over here is back. Bottom is here. And then the left side is over here. Behind the front here.
Okay, and why were the front, bottom, and front? Front, bottom, and
the front, the bottom, and the back are 0 because the magnetic field is running across the surface 90 degrees to this normal. So the front, bottom, and back all look like some surface with this vector with this A vector going this way and the B vector doing this. And so, or another view of it would be you got a surface that's this way, and so this A is going that way, and the B is doing this, which means they're that, and so you end up with a cosine of 90 degrees.
So the left and the slant, because they are perpendicular to the
left side. The left side is the left side is perpendicular. The right side is not perpendicular, but it's not parallel either.
But it's at some angle. Yeah.
It's at some angle, yes. It's at some angle such that its normal is not perpendicular.
Okay.
Yeah. All right. Any other questions there?
Nope, that was it.
All right. All righty. Let us take 5 minutes. Resume the recording. So, I have selected one more problem. Of interest to me, because once again, y'alls are, for the most part, physicians and physical therapists. Physicians might find this a little more interesting, though. Number 4. So, in certain cases, for reasons whatever, this would also happen to be a possible way of measuring. So, y'all's might be more interested in this as a way to measure blood flow in arteries and veins. I'm not sure how useful that kind of information might be. In an industrial process, people want to know how fast stuff is moving. I can see that being quite useful to them. In fact, I have seen such a flow meter. I don't know if I've seen a flow meter like this one, but I have seen flow meters in industrial processes, and so I know they like them a lot. So they might consider this a similar solution. So we have a blood vessel. Try that again. In a uniform magnetic field. And we're going to put electrodes across our blood vessel. And we're going to measure the voltage, I believe. Oh. Blood goes in. Blood comes out. Good heavens. Drawing shows a type of flow meter that can be used to measure the speed of blood in situations when a blood vessel is sufficiently exposed, such as surgery. Dang it. Blood is conductive enough that it can be treated as a moving conductor. When it flows perpendicularly with respect to a magnetic field, as in the drawing, electrodes can be used to measure a small voltage that develops across the vessel. Suppose that the speed of the blood is 0.3 meters per second. The diameter of the vessel, in particular, this way. Diameter of that blood vessel is 5.6 millimeters. Our magnetic field here, E, is 0.6 Tesla. In a 0.6 Tesla magnetic field, what is the magnitude of the voltage that is measured with the electrodes in the drawing? Ah, yes. Okay. So, this is a case of using our motional EMF, which is is equal to VBL. There it is, VBL. So we got velocity of 0.3 meters per second, a magnetic field of 0.6 Tesla, and a diameter from side to side of 5.6 millimeters. To get this out in sensible units of volts, I need this to be in meters. So that'll be 1,000 millimeters per meter. Millimeters cancels meters. And I got Tesla meter squared per second. That sounds like Weber per second. So I suppose that's a volt. So 0.3 times 0.6 times 5.6 divided by 1,000. And we get a tiny little number, 0.001 volts. I suppose you can multiply that by that would be 1,000 millivolts per volt. Volt cancels volt, and so that turns into 1 millivolt. So not a whole lot, but it's something. Yeah. Questions? Makes sense? So obviously, there you can do your dimensional stuff with this and turn it into a flow rate, and figure out how fast that, how much blood that is, what volume that is. So that'd be volume per time, and so that you get so that'd be 0.3 meters per second times the area. That would be pi d squared over 4. So that'd be 0.3 times pi times d 5.6 over 1,000 squared divided by 4. Not very much. That's a slow leak, if they're leaking. Times 10 to the minus 1, 2, 3, 4, 5, 6. Well, I suppose, but it's in cubic meters per second. So perhaps not as bad. That's a tiny number, but it's also in cubic meters, and that's a lot. In more useful units, milliliters, that's a cc, cubic centimeter. Let's go with 100 centimeters per meter cube times 100 cube. I don't know, maybe that's a pretty good leak. 3.79 milliliters per second. That sounds like a good leak. That sounds like a pretty good leak that you might want to stop. If they're leaking. If they're doing what they're supposed to be doing, whatever. Anyways. Questions? Make sense? Alright. That was my pre-selected questions from the book. Y'all's have an exam next week. Let's see what my inspiration is thinking about when it comes to exams. Or one of my sources of inspiration. We got an hour to try one of his. Dr. Ford, where are you? Let's go back on this one. No, let's go back on this one. There's the format sheet. Format sheet. Oh, come on. Nope. Don't go back. Don't go back more. You know, go forward. Old exam 1. Let's go ahead and grab the 2015. Alright. Oh, let's grab this guy. I like this one. Let's start here. Nope, don't do that. Print screen, there we go. Grab that. Paste it over here. Yep, do that. And make sure there's no more further questions in here. Is there part C? There is. Alright. Let's grab that as well. Grab that. Paste it there. Nah, not there. Let's put it here. Good. And then we'll grab that. And we'll paste it up here. Alright. Back to here. Very good. Alright. So, having run out of material, pre-select material, let's start reviewing for the exam. So I have grabbed a capacitor question here from, this is Dr. Ford's, let's change that over. Not you. You. What have you done? Who knows? No idea. Alright. So, we have three capacitors. Number 1 is 6 times 10 to the minus 6 farad. Number 2 is 12 times 10 to the minus 6 farad. Number 3 is 5 times 10 to the 6 farad. And are connected to battery V. As shown in sketch, after the capacitors reach their final charges, voltage across this guy is 24 volts. Calculate these things. Okay. Alright. So. Yes, here. Okay. So. Okay. Alright. So this is something I suspect I have failed to mention as a concept. But it's quite helpful to us. Let me grab my capacitor questions. There we are. My capacitor equations. These guys right here. Is that all of them? I think I'm missing some. Alright. No. Is that all of them? I think those are the ones I care about. Move it to there, drop it down. Okay. All right. So, the idea that I failed to mention, mostly because it's been a hot minute since I've discussed capacitor, since I've fully talked about all the ideas of E&M. So what happens here? This battery here, not you. I want this one over here. The battery here will put out positive charges this way, and put out negative charges over here. And so, what's going to happen is that charges are going to end up piling up over here on this side, and minus charges are going to pile up on this side. Well, these minus charges came from somewhere. And so these minus charges actually came from this side over here, which means that two capacitors that are in series like this will have the same Q on both of them. So the Q that ended up on this guy had to come from this guy here, And the Q that's on this guy had to come from the battery. So that means that Q on capacitors in series are the same. The same idea happens for resistors. So I in resistors, because the current can't go from, it has to come from somewhere. Because the current has to come from somewhere, any I in one resistor in a series has to be the same. Alright, now we've got that taken care of. Now we can figure out the voltage across C2 using this guy here. We know the capacitor. The first thing is we need to find the Q on the first guy, so we can find the Q on the second guy. So Q1 is equal to V1 C1, and we know those. We know the C. The C1 is 6 times 10 to the minus 6 farad, and the voltage is right. Dang it. Has been provisioned to us as 24 volts. So now we know the charge. 6e minus 6 times 24. Dang it. Alright. So it'll be 1.44 times 10 to the 4 minus 4 coulombs. Well, as noted, that has to be same for both of those, so that'll be also Q2. So now I can find V2. This guy right here. V2 is equal to Q2 over C2. So that's 1.44 times 10 to the minus 4 coulombs divided by C2, which is 12 times 10 to the minus 6 farad. And so that'll be divided by 12e minus 6. So that's 12 volts. 12 volts. All right. So this guy here is 24 volts. And this is 12 volts. And since if we went to a loop around here from Kirchhoff's loop law, that must be 0. So we have 24 here, 12 here, and then negative some V here. And so that would be 24 plus 12, 12 I say, is 36. So this guy here is 36 volts. Well, that's also the same as this loop right here. So that's the battery voltage, 36 volts. But we also needed that for this guy here as well. So what do it want? It wants the Q. Yeah. So we're back to Q3 is equal to V3 C3, which is what we needed for this guy as well. Okay, good. I didn't make that number up for no reason. 36 volts times the capacitance of 5 times 10 to the minus 6 farad. 36 times 5 e minus 6 is 1.8 times 10 to the minus 1, 2, 3, 4 coulombs. 1.8 times 10 to the minus 4 coulombs. We got questions about that? Makes sense? Hearing no questions.
So, I mean, I'm trying to think of. I didn't get a lot there. I'm trying to think of the right question to ask, I suppose. So, I got confused around the part where you use Kirchhoff's loop law on to deduce that the C3 and battery loop must equal the other two.
So it's not that
Going on
they
there?
equal the other two. Let me go grab the image again. What? Where is he? Here. Go grab the image. Print screen. Just that bit there. Copy that down. Come here. Don't do that. Paste it. Very good. Move it over to somewhere with a little more space. Alright. Oh, we got a little bit of hanging on around here. Go away. Thank you. Alright. So, we have Kirchhoff's loop law here. Alright. Going like that. So this guy here, that was 24 volts. And this one was 12 volts. You go around your loop. So you get V1 plus V2. Well, this guy's going backwards against things, so he's actually minus V3 is equal to 0 volts. So that's V1 plus V2 is equal to V3. So that's 36 volts right there. And then the other loop law is grab this guy here going this way, right? So then we have V from the battery plus, is that minus? That'd be minus the capacitor V3 is equal to 0 volts, which means that V of the battery is equal to V3, which we already knew to be 36 volts.
So, okay, so there's, because it's parallel when it splits to C1, C2, and it goes back to a single line at the end, you could effectively be saying that there's two loops where it goes one way or the other way, and those ways are equal.
Yes, correct. I think a better way to, dang it. Yeah, a better way to be drawing this would be, nope, don't do that. If I were to draw it, I'd recommend drawing it like so. Because in my opinion, this way emphasizes that this from, to me, because of my experience with this stuff, I know that the voltages from anything on this line to this line has to be the same. So the voltage over the battery, voltage over V3, voltage over 1 and 2, those all have to be the same, wherever they are. So 36 volts there, there, and there. So this immediately draws out to me the equivalence from the left side to the right side.
Yeah, that I agree with you. I think had it been drawn that way, it would have been a lot more intuitive.
Yeah. So, I mean, there's nothing wrong with what Ford did. It is correct. And it's probably, you know, if you were to actually make that kind of circuit somewhere, you know, what often happens is you got your voltage, your power source a long ways over here, and you got your stuff that's doing things way over there, and so kind of your circuit will kind of look more like this physically. But this emphasizes a equivalence, a constant voltage appearance between the left side and the right side. So this would probably be a more clear representation of the circuit. Here's that. Any other questions?
Nope.
All right. Get rid of that guy. Select none. Thank you. All right. Next question down. Look like it has a resistor network. Come on. Current through that resistor and that battery there. Okay. Yeah, let's grab that one. Don't do that. Do this. Put that over there. Drop it down. I'm going to grab C, but not D. Yeah, we'll grab that one. Control X, Control V. Move it up to here. Alright, I'm gonna make my own D, right? So got the current there, the current there, the current there. Yeah. I'm gonna make my own question. I think we want to make that text 20 instead of that. D. Yeah. If I spell right. And nope, don't do that. Okay, I need my where's my recently closed? Bring that back. Bring it down, and then give me back my pencil. Thank you, and go away. All right. All right. So. All right. Alrighty. So. Oh, 10 minutes. Uh-oh. Alright. I gotta be quick about this, don't I? So, Kirchhoff loop law going this way. So this 24 volt here means there's 24 volts going through there. So that means that's the so that's the current for this guy. So we have that V is equal to IR. I is therefore equal to V on R. So that'll be 24 volts divided by 3 ohms is 8 amps. Alright, 8 amps. And that'll be going this way. Alright. So, if we have 24 volts here, that means we also have 24 volts here, but we got 10 volts across that. So between here and here, do you want to do it that way? This here. There's ways to do this. So 24, that'll be 14 volts here. So what should happen is I'm going to say that it's probably 7 amps there. And so it'll be 7 amps there. But let's be careful about this. Make sure we do it right. So we'll do a Kirchhoff loop law here. So that's 10 volts minus 2 ohms and our current, and minus, yeah, I think I screwed that up. As in, my claim that this being 7 amps is not correct. And so minus, that'll be 24 volts there. So good thing I did this right. Did this up properly with the Kirchhoff loop law rather than going, I think it's 7 amps. I'll wager he's anticipated this. So what do you got going on here? This guy here from there. No, maybe it is. So we got minus 2 amps. I. This from that is minus 14 volts. 0 volts. So 14 volts is equal to minus 2 ohm I. Divide it over, and so I is equal to 14 volts over 2 ohms with a minus sign is 7 amps. So I was right, it's 7 amps. But I think it's going backwards. So that's my sign here says to me that instead of going this way, the current is actually going that way. And the current through the 24 volt battery, so we got 7 amps going this way and 8 amps going that way. So this guy's got, so we got 7 amps going here and 8 amps going here. So that means we got this much current going that way. So 8 plus 7 is 15. Yep, there it is. So we got 15 amps coming out. 15 amps coming out. Going in, coming out. And it doesn't matter. Okay. So that actually the signs on these does matter to this guy here. Power supplied by the batteries. All right, so power is equal to V times I times V, V times I, whatever. So that'll be 24 volts for this guy over here. And he's supplying 15 amps. The other battery, this guy here, he's actually receiving power. So he's minus 10 volts at 7 amps. If I read this right. Now we're going to find out that this is going the way I think it does. 24 by 15 minus 10 by 7. So that's 290 watts. Alright, and the power consumed by the resistor? Well, okay. So this guy here, he's got power, in that case, is I squared R. Is one way to do it. That's a good way for this guy here to be I squared R. We'll go ahead and do the IV on the other one. Right? Yeah, we do IV on that. For the other one there in the middle. So let's see, we got 7 amps squared. 2 ohms plus the I, 8 amps and 24 volts on the other one. So that's 49 by 2 plus 8 by 24. Huzzah. I am delighted. I got it right. Or as I did produce answers that don't make sense. So, so this guy is producing. So this guy over here, he's making 360 watts. And the other one, 290 minus 360. Yeah, he's consuming 70 watts as he's charging up. And then the two, that means that the net power produced by the batteries is 290 watts, which is matched by the power consumed by the resistors of 290 watts. It all makes good sense. We have made 290 watts and we're getting rid of 290 watts. Ta-da. Questions? Makes sense? Alright. Hearing no questions and seeing 1 minute remaining for class, I will conclude that here, and I will see you all on Tuesday.